Why is quantum tunneling hard to verify experimentally? Imagine a tiny particle, like an electron, suddenly appearing on the other side of a barrier it shouldn't be able to cross. Sounds like magic, right? That's what quantum tunneling is all about. It's a strange effect where particles pass through barriers they don't have enough energy to overcome. This phenomenon is behind many cosmic mysteries and even the way your computer chips work. But proving it in the lab isn't as simple as it sounds. First, quantum tunneling happens at an incredibly small scale. We're talking about individual particles so tiny that watching them directly is nearly impossible. Instead, scientists look for indirect signs, like changes in electric current or the likelihood of particles appearing on the other side of a barrier. These measurements are statistical, meaning they're based on many particles rather than a single event. This makes it tricky to pin down exactly what's happening during a tunneling event. Second, there's the question of how long tunneling takes. Some experiments suggest particles tunnel faster than the speed of light, which seems impossible. But this is more about the strange rules of quantum probability than actual speed. Different theories give different answers about how long tunneling lasts, and experiments often produce results that are hard to interpret. This makes it difficult to confirm a precise tunneling time or mechanism. Third, the environment around the particles complicates things. Tiny electromagnetic fields, temperature changes, and vibrations can all interfere with measurements. To get clear results, scientists need to isolate their experiments in extremely controlled conditions, often at very low temperatures. Even then, they usually observe the average behavior of many particles, not the quirky details of a single tunneling event. Fourth, the nature of quantum mechanics itself makes verification hard. It predicts probabilities, not certainties. You can say how likely a particle is to tunnel, but not exactly when or how it will do so. Some interpretations suggest particles have specific paths during tunneling, but these are nearly impossible to see directly because measuring them disturbs the system. This adds another layer of difficulty when trying to verify the process. Fifth, many experiments use analog systems instead of real particles. Scientists might use light in waveguides or other setups that mimic tunneling. These experiments give useful clues but aren't the same as watching actual particles tunnel. They're more like a quantum-inspired simulation than a direct proof. All these factors make quantum tunneling a tricky phenomenon to pin down. It lives in a world where particles act like waves, where probabilities rule, and where observing too closely can change what you see. It's a realm full of surprises, where barriers become semi-transparent and the idea of speed gets fuzzy. Despite the challenges, tunneling is everywhere in nature, powering stars, lightning, and even the tiny electronics in your phone. It reminds us that the universe often defies our common sense, and understanding its quirks requires patience, clever experiments, and a bit of quantum curiosity.